In previous videos, you learned how to create machining setups and looked in-depth at Fusion's adaptive clearing roughing strategy. In this tutorial, let's delve into some of the basics of creating toolpaths to turn your designs into machine components. Fusion 360 organizes operations into 5 categories. 2D operations, which contains operations aimed at cutting parts with prismatic surfaces, meaning parts with vertical and horizontal faces. 3D operations, such as parallel and scallop, for machining parts with more free-form surfaces. Drilling, which can be used to program holes from simple to tapped to compound holes such as counterbores and countersinks. Multi-axis operations that use more than 3 axes of your machine simultaneously. Finally, probing operations to ensure your part is located properly on the machining table and to verify your operations and the accuracy of your machine parts. Notice that each operation has a tooltip when the cursor hovers over it, giving more information about that strategy so it's easier to choose between them. We'll start out with a simple 2D facing operation like you saw in the last video, but taking a closer look at the 5 tabs: Tool, Geometry, Heights, Passes, and Linking. Every toolpath in Fusion 360 uses these tabs, which makes the programming workflow consistent even as you make more and more complex toolpaths. I'll work through the tabs from left to right, starting with the Tool tab. In this case, we're going to use a 2-inch face mill, and I'll use the filters at the top of the tool library to find it quickly. When I select the tool, the feeds and speeds are automatically updated based on what was set in the tool library, and I can fine-tune them for this operation if desired. The next tab is Geometry, where I'll make any necessary geometry selections. In this case, I don't need to make a selection, as we want the toolpath to go to the stock extents which are automatically pulled in from the setup, shown as a yellow rectangle around the part. The Geometry tab also lets you define a tool orientation for positional multi-axis, which we cover at length in the positional multi-axis course linked in the corner now. The Heights tab limits the toolpath in Z with top and bottom heights, as well as defines the clearance, retract, and feed heights. For this facing operation, we want to remove the material from the top of the stock to the top of the model. Any of the heights can be set relative to another height, or can be set using a selection directly from a model or sketch. If you'd rather set the heights visually, you can simply drag the heights into position. The Passes tab defines how the tool goes about removing material, including parameters like step over, step down, and more that relate specifically to the selected strategy. For facing, we can set a pass extension to extend the tool past the machining boundary. The last tab contains the linking, lead, and transition options that control how the tool enters, exits, and moves between cutting passes. At this point, we can press OK and view our toolpath in the graphics window. We covered creating 2D adaptive clearing for this part in the previous video, so I'll skip ahead to machining the inside of the component. Let's use another adaptive clearing, and again start by selecting a tool. Next, we can move on to the Geometry tab and first select the pocket contours using a model face. Since we've already removed the material from the outside of the component, I'm going to specify a stock contour. Stock contours define the outer limits of the toolpath, ensuring we're not performing any unnecessary cutting moves and optimizing our toolpath. It will also ensure that the material will be removed across the top of the circular internal pocket regions. Rust machining can be used to avoid cutting fresh air if we've already removed some material using a larger tool size. We can now move to the Heights tab, and we can see that the default bottom height is automatically set to the contour we have selected. As we face the top of the part, the top height can be set to the model top. This time, let's enable both ways to ensure we are both climb and conventional milling. As this is a roughing toolpath, let's specify stock to leave to cut with a finishing pass later. This can be defined both axially, which is along the tool axis, and radially, which is perpendicular. Lastly, let's look at the Linking tab. Again, we have a few options this time, including the ability to set ramp options that control the vertical transition between different levels in the toolpath. I'm going to modify the retraction policy, which controls how high the tool will move before transitioning to other toolpath sections, and the stay on level, which controls the likelihood of the tool lifting between sections. Remember, hovering the mouse over the parameter provides more details on what the parameter is and how it works. At this point, we can take a look at the toolpath. I'm going to follow the same principles to program a few more operations, to remove the material from the inside of the component as well as finish the outer profile. Remember, the 5-tab system means each toolpath is easy to understand, allowing you to find the parameters you need to dial in each toolpath. Now it's time to program some drilled holes, and we'll see how drilling differs slightly from other milling operations. In the Geometry tab, you can select faces, points, or a diameter range to define the holes we want to cut. I'm going to use faces and graphically select the cylindrical surface that represents one of my holes. I can then use the Select Same Diameter option to also include all the other holes in my model that are the same diameter. Advanced options like boundaries, additional selection filters, and ordering help you select and optimize your drilling operation quickly. The Heights tab looks familiar, with the added option of Drill Tip Through Bottom, which drives the shoulder of the tool to the bottom height rather than the tooltip. The Cycle tab is where you can change the type of drilling cycle you want to use for these holes. Each hole type is mapped to the machine can cycle automatically by the post when possible, ensuring safe material removal from the holes. Again, I'm going to use the same workflow to program spot drill and tapping operations. At this point, Setup 1 is fully programmed, so we can take a look at a quick simulation to verify our programming. As you can see, we are now ready to move on to Setup 2 and continue programming our part. We have already programmed a facing operation for the second setup, so I'm going to begin by creating a roughing operation to remove the bulk of the material. Due to the freeform surfaces, let's use a 3D adaptive clearing, which will be generated using the model surfaces. Even though we are using a 3D toolpath, we are still presented with the same 5 tabs. In the Geometry tab, I'll select a stock contour to keep the toolpath within the remaining material since the outside was roughed in a previous setup. For the heights, we can use an edge from the model to define the bottom of the toolpath to prevent further duplicate machining. In the Linking tab, I'm going to define the horizontal radius with an expression. If you right-click on any box, you can choose to define the parameter using an expression rather than specifying an exact number. This expression can use a range of operation or tool variables, and in this case, we can use 15% of the tool diameter. This parameter will now update if I make a tool change, meaning the toolpath will parametrically adapt to match my intent, saving me downstream work if there are any changes. Now let's take a look at some 3D finishing operations. 3D finishing in Fusion 360 is quick and intuitive since containment can generally be selected directly off the model. On this part, we're going to take a look at 2 tricks when working with tool containment, namely when there is a steep edge at the boundary that can cause a lot of noise. To start out, I'll select the ball end mill and then select the machining boundaries dynamically from the model. Note that when a boundary is contained inside of another, the toolpath generates between these 2 boundaries. We can now customize how the tool will behave when it reaches these boundaries. First, we can set the tool containment to Tool Center, which means the tool will be driven until the center of the tool touches the boundaries we have already specified. Don't forget, we can use the tooltips to fully understand each parameter. Now, I'll check Contact Point Boundary, which drives the tool contact point to the boundary rather than the tool center. We're now going to use an option we haven't used so far, Avoid Touch Surfaces. Since we have already finished the horizontal surface at the top of the model, we can set this as an avoid surface with a clearance of 0. Note that the Touch Surfaces checkbox allows us to invert the meaning of avoid surface, so the surfaces selected are targeted instead of avoided. In the Passes tab, I'll use an expression to drive the step over, setting it to be 10% of the tool diameter. For the linking, we can again change the retraction policy to minimum, and we're ready to take a look at our toolpath. As you can see, we are getting some noise caused by the steep fall-off at the edge of the boundaries. To solve this, I'll edit the toolpath by right-clicking and selecting Edit, navigating to the Geometry tab, and setting an additional offset equal to the negative tolerance. This will keep Fusion from looking over the steep edge when it generates the toolpath, reducing the noise, and we are left with a much smoother toolpath. The last area of the model we need to program are the 3D chamfered edges. To do this, we'll hijack another 3D operation, Scallop, which creates passes at a constant distance from one another by offsetting inwards along the underlying surfaces. For this chamfer, let's use the same ball end mill we used in the last toolpath to minimize tool changes. By searching the document tool library, we can see the tools that have been used in other toolpaths, and we can even look at which operations we use them in. For the geometry, I'll select the inner and outer edges of the modeled chamfer, and once again specify that the toolpath be contained by the tool's center at the boundaries. Again, we can set an offset equal to the negative tolerance, which will remove the noise at the boundaries. We want to enable contact point boundary, and this time we can specify a boundary overlap of 0, which will avoid any unnecessary cutting moves. In this Passes tab, the step over can be set to 25 thou, and the retraction policy in the linking tab can once again be set to minimum retract. Let's take a quick look at another stock simulation to make sure we're happy with everything and there's no collisions, and it looks like we're good to go.